Yeah. Boom. Welcome back, friendo. Just turn that down a little bit. There we go. That should be better. Hopefully that's okay. Oh. The pandemic continues. The hair gets longer and longer and longer. Good times, though. Good times. Ready for some Haskell hacking. Feeling good, feeling strong. Sorry having to delay my usual time for a couple of weeks in a row, but them's the breaks. Happens sometimes. Let's get to it, shall we? Today, we're going to continue on with our BTree, making progress on it. I think we're going to implement find today. That's kind of like the first step in the algorithm for insert on B trees and B plus trees. So let's get to it. Good old store BTree. That's the one I'm on. All right, so find, because everything's ordered, is kind of like binary search. It's a little bit different though, because when we're searching through the nodes, we've got, they're different, like the number of keys and the number of child elements are different. Because when we're searching, we've got to search between the keys. All right. I'll explain a little bit more about that in a minute. So we got that. Let's open up the test file for this puppy. BTree. Cool. All right. So, find. When we have a node, say 4 elements in it or whatever, right? We've got 3 keys. Say C, F, I don't know, K, and S. Could have chosen some slightly different ones for 4 letters, but it looks pretty good. And the childs are all here. So there's the size of this, right, is 4. But the size, so the size of this here, from here to here, is 4. Right, and each of these under here, each of they could be leaf nodes, it could be other nodes, whatever, the childs. All right, we're representing internally as a vector. The size of that vector here is going to be 1 greater than that. So it'll be 5. And when we're searching for a particular key, we're looking for the element that is between the 2 keys, or off on the side if there's no other one, betwixt keys. So the idea is that if we're searching for D, right, we're going to search in the keys here first. Right, we're looking for D. We're going to search in here, and we're going to find that, well, we're not going to find D, right? So where should we go? There's still more of the tree to explore. Well, we're going to go, D is greater than or equal to C, but it's less than F. So we're going to search down here for D, and it's going to search in this node, this tree, this part of the tree for D. And it's going to be the same thing until we hit a leaf node. The leaf node is just going to search for the keys, and if it's there or not, then we know if we found it or not. So if we find it in a leaf node, then we found it, and we're good. If we don't find it in a leaf node, then it's not in the tree. So we really have those kind of two cases to handle, leaves and nodes. And in the overall algorithm, kind of the big picture of it, once we zoom back out, is that we find where to insert D. Right, so if we want to insert it down here, we look for the key D. But insert, we shouldn't find it. Right? We should get to a leaf node and find the node there that we want to insert it into. And then insert it. Right? And then we do all the other operations that we've been working on. If we need to split, we split, merge up, split, merge up, split, merge up until there's no more splits to do. And then we unzip the tree, take out our data structure from the zipper, and we're good to go. All right, so this find operation with our is going to be basically like a zipper operation like our other ones, I think. And that's because we're going to, when we write insert, we're going to zip up the tree we're given. And we're going to have to implement all this in terms of those zipper operations. All right, so every time we find and look for something, we have to go down. We're going to put that on our breadcrumbs so that when we have to like do that merge up and stuff that we did before, it's going to just use the zipper and those crumbs to find its way back up to the top and to the root, possibly splitting along the way. And merging and all that fun stuff. And yeah, so I think for our find function, what we want to do is we just want to find the leaf node that we want to insert into, given that key. And the return of that find operation should be a zipper focused on that node. Make sense? Hope it makes sense. So let's start with a test. Spec that out. Make sure we understand how it's supposed to work. Write out how it's supposed to work. And then we can get to trying implementing it. So where to put it? Let's just make sure I'm actually up to date on the code on this machine here first. Let's fetch. Might have done some work, I'm not sure. It's hard to know these days. One day bleeds into the next. What can you do? I think we're probably good. Yeah, okay, cool. So where should we put it? Zipper. Let's insert leaf. Let's go inside zipper. We'll describe find. Yeah. Find. Okay, let's just call it find. I don't know. Lots of things named find. This is our find. It is unlike any other. So it should focus on the node we're looking for. Focus the zipper. I mean, it kind of makes sense because we're in the context of zippers. So start with a simple case. Let's choose pretty simple. One of these looks fine. All right, let's do that one. No. There. Okay, there's the root of our tree. Fabulous. Okay. So, when we've call find on this with a key, let's pretend we're searching for D. No, we're going to be inserting a key. We're not searching for a particular key. So maybe we should call it insert find. This is not a very good tree to experiment with. Exactly, but so let's just pretend we're searching to insert H. All right, so it should focus on this node down here at the bottom. Ah. Thanks for pointing that out. For some reason, OBS started up without desktop audio on my other thing, as I've set that up too. Let me fix that here. There. Reconnect. I don't know. OBS is acting weird today, folks. I don't understand what it's doing here. Desktop audio is active. Maybe it's just not loud enough for you guys. Okay, let me put it. Oh. I just had it really low. Hopefully it's a little better. Guys missing the chill tunes. That's what you're here for, right? Nice. All right, friends. Sorry for the distraction. Hopefully that works better. Just let me know, chat. Yeah. Audio is difficult in general. I have so many input sources and output sources on this machine. It's just bonkers. I feel for the app developers who have to support all this stuff. Ah, thanks, Checksor. It's nice. Hopefully my thinking is pretty straightforward and good. Sometimes I feel like I get in the weeds a little bit, but anyway, if we find, so we go H, we find H, what do we got to give that? The rest, we got to give it with a zipper up of the root. And if we unzip it, that goes back to the root. So this should be, oh, we might end up having to write out the whole zipper structure here. Yeah, that's okay. You know, we're not born knowing data structures, right? Some of them I focused on more than others, like the more common ones. This is not a very common data structure, so well, it's common if you do certain things, I guess, like databases and whatnot. I haven't done a lot of databases, so here we go. This is what we're here for. Yeah. Never fear. Haskell is here. All right, find H in the zipper of root. This is going to return a zipper back. Unless we have, like, pass it to first, because we maybe don't care about the trail. Unless we do. Let's just write it out. It's not that big of a thing. So this should be a leaf, order 3. Basically the exact same one we get here. This is the node the zipper should be focused on. And the breadcrumbs, the list of steps it took to get here, should have the parent node up on top. And that should be it. Put that there. That should be a crumb. The index it should go down to is 2. The order should be 3, just as we had before. And the list of leaves, the vector of leaves. Exactly the same. We might need to add that in some parentheses and kind of just clean this up for our own viewing pleasure. But otherwise, something like that. I don't like leaving hanging punctuation lying around, but I think that's okay. Kind of gets the point across. So it should look something like this, assuming this compiles and everything's good. So let's just run the tests and make sure that's good. Which library was that, Checksar? Curious to know. Oh, great. It's not crum's down 2. Crumb is the type. Down 2 is our constructor for the only crumb we have. Sweet. Okay, I can't find, so that's kind of expected. So let's go just, that'll probably fail with that. Yeah, that's good. So we'll just go back to BTree, put a definition of find maybe down here. So find is going to take a key, which I think is going to need an order instance, probably. It'll take that key, a zipper of KV, and it'll return a maybe. Zipper KV. Pure script precise. Nice. Huh. Nice. 0.1 plus 0.1. It's a nice error. Oh, cool. Yeah, not always true. There's a one I was discussing this morning, and I've heard it come up before in Haskell every now and again, and that's the hash map data structure. And so when you learn data structures, like one of the basic ones you learn are hash maps, right? And one of the things you learn about hash maps are like collisions and stuff, right? Like pretty rare, but they have the potential to happen, right? And so you get this little warning at the top of the library, right? It makes no guarantees as to the order of its elements. But there are ORed instances on hash maps, right? There's equality instances. And, you know, we were discussing, this came up because we were discussing, I think, hashing or something like that. And this data structure is used behind the scenes in ASON for the value type. So is it possible that you can get different results of hashing an ASON value and serializing it? Well, serializing the string then hashing it, you can get different hashes, potentially. I think in practice, it's like almost always going to be true that you, like almost always you're going to get like an ORed out of it, I guess, is the going theory. And that the potential for hash collisions is a theoretical possibility. So it's probably safe. It's probably okay to have an ORed instance on them, I guess, is the idea. It's curious though. So I think, you know, a lot of people will give Haskell some flack for being like a very like mathematical language and it's like, well, yeah, I mean, some of the theory underpinning it and stuff is there. I'm sure there's reasons why there are ORed instances here, and I'm sure they're probably more pragmatic than theoretically pure. And, you know, implementers of Haskell and GHC and compilers for it, you know, it's a complicated beast. Affordances and compromises have to be made. All right, so I totally get it. And that's why I think that statement, if it compiles, it works, is kind of like funny, I guess. Because then people get surprised when they encounter stuff and errors and things like that and whatnot. Thanks for sharing. That was fun. Yeah, so let's just get those tests going again one last time there. Get our match. Probably just move right into the server thing so I don't keep running the golden tests over and over again. Oh, right. Bob. Whatever. Okay. Yes, yes, yes. No, I don't want to become famous. How do I ban you? Thing. Well, Checksor, maybe you're about to become a moderator, so you can help me figure this out. There you go. Oh, I figured it out, but there you go. You are banned. Cool. Never, ever, ever, ever spam me. You out. Especially with the ads. I hate ads. That's why, like, I got affiliate, but I haven't turned it on. Don't want ads. Maybe that makes me a bad streamer because Twitch, I'm not making money for Twitch. I don't know. Who cares? They let me do it, I do it. Right, okay. So that should be good to go. Oh, right, it needs to be a maybe, of course, all wrapped up. Nice. This is all in parentheses, so I probably don't need that. Blah, 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 blah. Come on, let's go. Anybody else who wants mod who's been a long time viewer, just let me know. Okay, I'm getting type errors in my tests because I'm not doing this properly. Okay, maybe zipper. Did I not make that an alias? I did make it an alias. BTree list of crumbs. That should be it. Is it is it a parentheses issue with this thing? Something like that. Look, it's looking for a function. That's annoying. Vector, BTree, whatever. Something. That should be right. Once I get this figured out, we'll move on. I'm sure it's something silly. What am I doing now? Just insert the parentheses, please. Bam, bam. Probably just a little off from home row. Now, I picked up a new cat somewhere the other week. She should be around here somewhere. Oh, she's chilling out right now. Yeah, she's a foster cat. Well, no, she's probably going to become part of our family. But if you see her pop up here, I'll introduce you. Okay, maybe it's that thing. Let's just put this on file watch. Yeah, that's still there. That should be good. Maybe zipper. Da-da. The second argument of it. Yeah, okay, fine. Eh. Eh. No, that's gotta be right. Ugh, this is annoying. Let me put that there then and stop doing that. Don't care. Computer. Well, let's go. Oh, I hate this. Really got to get these type errors showing up in my editor again. Happens to me at work too. Like this project I work on at work is kind of large, and GHCID doesn't really, I don't know. I haven't really made it work with it yet. I don't have it there either, so I use GHCID, which some people really like. I haven't been able to get it integrated with my editor, so I kind of watch it in a terminal window, and that's like just super slow. I'm not happy with it. Need to fix it. Need to work on that. Tooling's important. But I hate fighting with tooling. It bores me. Okay, what am I doing again here? Come on. Yes, I do expect a zipper of something. Okay. I'm giving it a list of vectors. That doesn't seem right. Oh. Duh. Duh. Oh, gosh, I forgot. Of course. We're missing one of the vectors. We've got to build a node here. The parent has this vector in it. Oh my gosh. See what I mean? Long day. Not always the sharpest tool in the shed. But I don't know, like as an engineer, software developer, you know, I've had kind of a long career so far. There was a time in my life where I feel like when I was younger, I could just keep a whole ton of stuff in my head at once. And just the code would flow and it would just come out. And it's probably not entirely true. Like it's, you know, full of stuff and required fixing and whatnot, but I rely a lot more on tools these days to keep the complexity in check. Keep myself honest. There we go. When I was listening to Leslie Lamport just talk about TLA, he was saying kind of the same thing about age, as that, you know, the older he gets, the more and more he relies on math. I don't know. Is Haskell the boomer language? I'm not a boomer, but pretty, you know, between Gen X and Millennial, somewhere around there. But maybe. Elder Millennial language. Okay, so that should be good because it's failing because it's undefined. So let's go move on, implement find. Okay, so we've got our needle, our key that we're searching for. We've got those two cases we need to handle. Beleaf, which is the basic one. I don't think we care about the order at this point, so we're just going to ignore it. Leaf and the keys. That's all we care about here. And we also have the node case. It's going to be similar in construction. But we need the child's. Oh, and this is a tuple, right? So there won't be any childs to go down to, so we don't really. We might need. No. Yes. We might need childs here as well. Let's bring in a scope anyway. We don't need it. We don't need it. It'll show up, and Haskell will tell us, and that's okay. So same thing down here as well. Just got to pull apart this tuple. Top, child's, crumbs. Sorry, no, it's crumbs. So let's just call that C's. Cool. Let's just do the beleaf. The simple case is pretty easy, I think. So what do we got here? We have to hunt for that key. Do we have to hunt for the key? We just need to focus on the key. If this is a leaf that we can insert into, if we get to a leaf node. I think we're guaranteed to get to one eventually. So all we need to do here is return just. In fact, I don't think we even need to search in the keys at all. Just if we get to this point, we can actually just go that, this, and just return the zipper. Just return Z. I think that's right. Let me just think this out a second. All right, pop, 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 pop. It's getting bigger, 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 of course, because whatever. Burp, burp. We go here, 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 here. And we got more here, 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 here. Whatever, whatever, whatever. All right, the tree is always going to be the same height, because that's kind of what the whole purpose of this thing is. And we'll find here, we've got to go down to this part. We search in here, we've got to go down, I don't know, here. There's only one key in here. It's a leaf. So we can insert. Yeah. Basically, if we get to the bottom, that's where we're going to insert to. And if we implement find correctly, then we're going to get to the right leaf to insert to. So I think that's pretty, seems about right to me. So in the node case, that's the trickier one. That's the one where we do need to do the binary search on the keys and figure out which way to go. And then do move down to that node when we find it. Ah. Okay. key and keys. So we're going to search for the key in keys. What are we going to find? We're going to find an index to move down to. That's what search needs to return to us in order for us to make progress. So search would have to return an index. There's no case to match on, so it wouldn't be nothing. So in that case, we could maybe do it this way. Search. Nope. It will be a pure function without any maybes. Key and keys. We might not even need this here. And then what do we do? Well, now that we have the index, we can go move down to that index. So we still need to pull out Z here. That's probably why we don't need C's. Or childs, just the keys. We need to move down to X. And we also need to give it the zipper to move down 2. That's Z. And that's it. I think that's the whole formula there. The whole equation. Probably even get rid of this let binding and just do it all like that. Yeah, just put some parentheses around here. Okay. So search. Okay. Vector of such case and needs to return an integer. Cool. Probably still going to fail, obviously, because we have undefined in there, but search. Okay. So we're going to implement a funky binary search. The funkiest of binary searches. Papa. This is our vector of values. It's just to remind ourselves what binary search does and how it works. And if you haven't seen it before, maybe a poor introduction, but hopefully I do a good job explaining it. So we have our values. They could be anything in here. The only caveat is that they are ordered. And because of the order property on our tree when we're constructing it, we can assume this vector is going to be in order and sorted. So what we need to do is we start with our low pointer, our high pointer. So instead of searching one by one through the list and like potentially searching the whole thing, we're going to like take kind of a divide and conquer approach. So low and high refer to the indices, 1, 2, 3, 4, 5, and 6 in this example. And we take initially a midpoint. We start at the middle one. So a mid of 6 is going to be halfway, and we'll round up in the case of odd. indices. So we'll take 3 as our mid. And we have, okay, what we're searching for, say, I don't know, L. All right, we've got C, F, H, I, P, X, and Z. Super, right? So we take our mid value, that's the thing at index 3, and compare the two values. This is why they have to be orderable, because we need to know if this is going to be less than or greater than the value or equal to this value here. So we do a compare on it. If it's less than, then we know that the value is in the subarray or subvector or whatever you want to call it over here. If it's greater than, then we know it's over here. If it's equal, then obviously it's equal. It's this one here. We found it. Okay. So that's basic binary search. If you're looking for this thing, like L, then you either find it or you don't. In our case, however, we want to find the first index that is less than or equal to our value, I think, is how it should probably go. Because, recall, we're looking at the keys here. The child's vector is going to be down here. It's going to be 1 greater than. All right, and we want to find the right index into this thing, ultimately. 2, 3, 4, 5, 6, and 7. All right, so we want to map into this index down here in order to find which child to give into down 2. That's the wrong one, but you know what I mean. Cool? Cool. So in that case, if we're searching for L, you know, is that greater than or less than I? Right, it's less than. Right, or I, sorry, is greater than L, so L is going to be over here. No, right, sorry, H-I-J-K-L. L's greater than, so it's going to be on this side. There. Ah, I'm on it today, let me tell you. Right, so we're going to search over this way, which means we're going to make low the new, we're going to make low the current value of mid. Right, and just bump low up over here, and then we're going to search between calculate a new mid, find that one, until we narrow it down. We're not going to find L in this one. So if we find the first one that's less than or equal to L, that means like when we stop and we don't find it, low will be equal to high. Hey, Swarm Collective, welcome back. So if we don't find it, low will be equal to high. And if we play this one out, we're going to go here, here, and the mid will be 3 and 6. So mid would be 5. X is greater than mid, so it'll be down here. So we move high down to 5. And we narrow it down. And we have these two. I think we'll end up on P, which means we'll It won't equal L. It will still be wrong, but we'll have nothing else to search. So in that case, we need to find out if L is less than P, and we want 3. We want to map into 3. I think. Yeah, because we want to go like this side here. And if L is greater than or equal to P, then we want to go right to 4. All right, so that 0 over here maps to 0 down here. 1 over here should map to 1 here, potentially here. And that should map like this. Yeah. Pa, pa, pa. And then everything's totally mapped to everything, so we're never going to hit an out of bounds case or anything like that. So yeah, basically that's the case. We're going to do some funky stuff that you might not normally see in a typical binary search algorithm. Is like when we get to the case where low equals to high, and then we have to do that check and map it to the correct index. If we get to the case where we actually do find L, then we just take the right side case, because we're always kind of, the way we construct the trees, the key that we find, if we actually find it in the keys, is going to be on the right child of this key. And so it'll be in that leaf as well, or node, or so on and so forth. Down to the bottom. Okay, so that's my super, super awesome and messy diagram. Hope you love it. Let's write some code. So this is going to be okay. Okays. This is going to be kind of like our... Since this is an internal function, we should kick off low and high with the v.length of keys. So it'll be int, low and high. I don't want to change the order of the arguments. We'll change the order of the arguments later. I think that's good enough. Okay. So mid. Was it like high minus, or sorry, low plus high minus low divided by 2. I don't remember if we want to use this div function or what's... Cool. So that means we've got mid in scope now. High load mid, just like we described. We need to do a compare. The thing that we're searching for and the thing in keys that we just found now. This might tick me off a little bit. Indexing into vectors in Haskell. Of course, if you give me a bad index, that would be an error. So instead of just throwing an exception, I'm going to give you a value. I wonder if there's an unsafe one we can use. because that'll just be far more convenient for this algorithm. I think there might be... Yeah. Pull that in the scope. And that's kind of like we were talking about Haskell compromises in places. There you go. There's one right there. Right? And a totally uncompromising, super pure language probably wouldn't have that function available. Maybe it would be even impossible to write. Okay, so in that case, we have k's indexed at mid. This is a case compare on. That gives us three cases to match. It's less than, equal to, greater than. Cool. So equal to is pretty straightforward. That's just going to be index. Or mid. Less than or greater than is the other two cases. And then I think we have to handle... We still haven't said anything about when low and high are equal, which we still have to handle before we can even get to this part. And whatever, let's finish this formula, this equation here. So if it's less than, then we search k. For k in k's, we make low the same, but we make high the value, current value of mid. And if it's greater than, we make it mid plus 1 and high. Okay, so that's our recursive case. Okay. So then we just need to deal with low equals high. So this is the case where our pointers are, we've eliminated all possibilities and we've moved past anything. Right? We search k low to mid, and mid plus 1. We can get to, so mid should always decrease because we divide by low and high by the difference in 2. We always increase mid and go high in the other direction. So yeah, they should eventually cross. And this is normally where you would return like not found. But in our case, it's special. Then something else. This. So in the case where low is equal to high, case compare We need to compare the last value we've looked at, where we ended up in the search, with the key to decide if we need to go to either low or low -1. So the left or the right, vice versa. K to K is arbitrarily picking low here. Greater than equal. If we get equal here, we should have hit that here. Technically, we couldn't get equal here, but just throw it in there because of, you know, types. We could also throw like an error case here. We could throw like undefined, or that might not be. Yeah, we should be able to throw undefined in there. We might get a warning from our compiler, but we should never be able to hit that branch, I don't think. If I'm not mistaken about this. But if it's less than, then we want, I think, low -1. Otherwise, we just want low. Yeah. Okay. Oh, redundant bracket. Where? Oh, of course. Okay. Yes. Thank you. Sorry, some stylistic issues, and then I think we're good. Nope. A couple of type issues. Oh, sorry, I misinterpreted. Those are the parentheses you meant. Do. Cool. And survey says green. I'm still like kind of somewhat unsure, but I'm going green. Ah, red. Okay. What do we get? Oh. We got an index out of bounds here. Oh, that's completely wrong. Probably because we didn't mean length of keys. We meant length of keys -1. Zero-based indexing at all. Nope, still wrong. Let's see, what do we got? Okay, we expected B leaf order 3, leaf EFG. The first part's right. Nope, that's wrong. We focused on D. Okay. Good. I like getting errors. That's all right. Okay, we went down to... It's kind of nice, too, that we get like a little thing like what you actually did. We went down to index 1. We expected to go down to index 2. In that case. Okay, cool. That means... What does that mean? We went down to index 1. Maybe we meant, maybe this case isn't quite right. There might be some edge casiness in this. I switch to there. So that means it found an index to go to. It just went to the wrong one. We just chose the wrong one. And we're searching for H in our example, which is totally on the very, very right of the tree. So it should never choose more than the maximum, like out of bounds. Right, so it's good we got the mapping there. Correct for the right-hand case. So we should probably have an example where we got to search the other direction. So down the left side of the tree, just to be fairly certain. And then a case where we hit equals at the node level. Yeah. And just make sure that it's going to go to the right side of the tree when it hits a node, a key in the node, until we get down to the leaf. So in that example, it should focus the zipper on the rightmost node. Let's just do this again. Let's go with leftmost. So if we're searching for, we already have A in the list, so that's cool. So we expect this to be leaf order 3, basically this leaf. The down 2 should be 0. Keys are fine, that's fine, the rest is fine. Bam, bam, bam. Pass. It's gonna go green. Super. And one last one. It should focus the zipper towards the right. Yeah, towards the right, I think. Maybe a good enough description, and the code will say the rest. So if we change this to be D, then we should find the middle one. We haven't really used you yet. So let's give you a shot. Will you be our friend? Let's see. Everything else, sure, that should be 1. There we go. How easy to set up the unit testing framework? It's pretty straightforward using HUnit. So HUnit is the test framework I'm using here. I think the default stack template, if you use stack, sets up a basic test module for you on your behalf, but doing it from scratch is okay too. I'm using HUnit, or am I using HSpec? I don't even remember. No, I'm using HSpec. Sorry. HSpec. I'm forgetting everything today. Terrible. Yeah, this one's a pretty good one. What I like the automatic spec discovery. I'm using that. So it's a good thing to set up once you start getting a few test modules and you start adding them quite frequently. You just create a little spec file with this in it and use a certain naming convention for your modules, and then it finds them. Yeah, so if you're used to Jasmine, it'll be pretty similar. And it integrates with other testing libraries in the Haskell universe pretty well as having good documentation and stuff. So yeah, HSpec, super dope. Okay, we got a failing test here. That's great. Super, super. Okay. So we expected that leave D down 2 to 1. It went to 0. Okay, why did that happen? How could that have happened? Maybe. It's pretty flexible. There are like quite a number of choices in terms of testing frameworks, just like in the JavaScript universe, Haskell. So that's the one I started with and kind of one I've stuck with. I've heard good things about Tasty. Not sure. So in that case, maybe mid +1 is the one we want, because we want to go to the right, which I think makes sense. I've assumed mid, when we're doing the binary search, mid was kind of like the rightish side of the current node, the mapping, but it turns out mid +1 is kind of the same thing up here. It sort of matches, which is about what I would expect. Correct implementation. So let's look. A green. That can be pretty nice too. I haven't done a lot of doc tests since my Python days where it's not as great. But I should give it a try in Haskell land. Cool, green. Yeah, so we got find. Finding around in our node. It goes to all the correct leaves. So, I think we can mark that off as done. Yeah. So the idea of the test beside the code, with the code, I like that. I don't know, like, have you a lot of experience with using doc test in Haskell, and what about it do you like? So when I was using it in Python, I found, one, it was a DSL buried in comments, so you didn't get any editor support for writing them in to begin with. And it just made my code a bit noisy because I tend to write a number of test cases. But I feel like I write fewer tests in Haskell overall, so it might be better in Haskell. Not sure. So maybe it's the same thing in Haskell too. Let's see. I care a fair bit about readability, and by readability I mean like like reading the code, I'm able to understand what it means, like denotationally. And sometimes having the spec handy helps clarify readability, because it kind of shows you by example what it does, and then because they're tests, they're executable, so if you change the code and you forget to update the documentation, Well, you can't get out of date with it, so seems advantageous. Okay, doc test. Oh, it does look at source code comments, just like in Python. Ah. Right? Well, yeah. For small stuff, I can see that being pretty useful. Which is usually where I ended up using doc test a little bit in Python, is like where I didn't want to really set up a whole package and test modules and all that stuff. But I mean, you still kind of have to do that with this anyways, because you have to, it's a package, right? Yeah. I can see a combination of it being pretty useful. For sure. Maybe we'll do that in this project. Or if somebody wants to contribute to Rosby and do this for Rosby, that'd be cool too. If I don't get around to it myself. Because then, yeah, when you're reading the module, you can get a couple quick examples. And if you're, I assume also this will export to Haddocks as well. So your Haddock documentation would have a couple of test examples too, which could be super useful. Yeah, I kind of like that, I think. Bot-wise, yeah, that's a good question. I'm not sure. Cool. Thanks for sharing. Okay, so now insert. We don't have a huge amount of time, so I don't know how far we're going to get into it tonight. The gist of it being... Oh, did I close Epic Pen? I closed Epic Pen. Boo. And somehow I brought up this keys. I mashed them like a puppy. Okay. So we're going to zipper up our tree that we start with. I think, yeah. We're going to call find. Find is eventually going to focus us on the leaf we need to insert into. I'm not sure at this point, though, how we're going to compose this all together. Supposing we go this way, and we end up at this leaf down here. So supposing find focuses our zipper down here. Yeah, one application find will end us up down here when we write insert. So the next function that we can pass this zipper to, maybe we need to use, I was kind of thinking we might end up doing something like this actually, where we implement, like maybe merge up was just not quite enough. Like maybe we need the zipper operation to also be the one that handles, once we get to find, we pass that zipper into that function. And, or maybe we just call merge up from here, and then merge up also handles the recurring going back up the tree and unzipping when it hits that case where it doesn't need to do any more merges, and just unzip. Because I think, yeah, let me look at that code again. Actually, let me just commit this because that's in a good state. And then we'll look at that code again. I'm kind of excited where this is turning what this is turning into. Took a while to get here, but I'm feeling pretty positive about this zipper business. Okay, so we added the find zipper operation to focus on the leaf node we need to insert into. Booyah. Yeah, I think it'll be really cool to see it, the final form. At least the first pure version. It'll be nice to see when we finally get that moment. There's still going to be quite a bit of work to do once we're done. Once we get the pure version done, I think we're going to need to... Well, we'll stop. We'll stop and take a breather. And we'll talk about performance a little bit. Because I feel like at some point in time, in order to implement this efficiently, we're going to need mutable vectors. And that's just going to require I/O and putting a monad in it. So, but only if we need to. All right. I think we can actually probably figure out what the ON case of this, if it's like on par for what a BTree should be or not, based on how we implemented it. Hopefully it's not too bad. But anyways, I digress. I mean, there's other things to be concerned about, but I digress. Let's move on. We'll do that. Maybe we'll take a break from that to do it, or we can just move right into the store, implement this entirely with Pure, and then start optimizing from there once we get kind of like the rest of the server in place, even if it's totally inefficient. Right. Okay, so back to our test module, because we should always start with a test. That's what we want. I think we can finally... Do we need to finally do insert? Oh, we wanted to review merge up. That's right. Sorry. Skipping ahead here. All right, so let's merge. And when we wrote this, we did a move down. We pass it to merge up the split node itself. And merge up has no concept of splitting. It's kind of expecting something else to do the split and to give it the split node. And I'm thinking if I do that from insert, right? We'd need... Well, we could do this like in a do block. Because a lot of these operations are operating on our zipper on maybes. So if insert returns a maybe zipper, if we write it as a zipper operation, we should be able to do it that way. We could write it like this. Say word K. Some value V. We give it a zipper KV. And it returns maybe zipper KV. We could do it like this, where we like focus leaf, or our insert leaf, the leaf. We find it based on the K and the zipper. This is terrible. By the way, that's a type signature. So we call key on Z, and then why would that not be good? Oh, because data list, whatever. Right, we get LF. We could do that way. But then we have to, like, do the recursion ourselves here somehow, right? Like, go to that leaf. What do we do when we have an insert leaf operation, right? That splits it. Or returns maybe the split thing. Yeah, it's equal to this. So we can insert into, no. No, that just inserts into a leaf and if it was successful or not. Well, that might not even be a useful function at this point anymore. Some part of it's going to be useful, but I don't think this is quite right. Merge up. All right, that's the one that expects something else to do the splitting. So I guess I don't have that. Insert key, insert childs. Okay, so we have some hypothetical function that, you know, we do a case on, right? Leaf split. Either insert or split. Right? And or leaf. K in the V. In the left case, pretend, let's say that it didn't need a split, it just split. Or it just inserted and it was fine. So in the cool case, we just need to what do we need to get? We need to get something here. I don't know yet. In the right case, though, it is split. Oh, in the cool case, that would probably maybe just return either insert or split returns a tree. Yeah, a leaf node of some kind. In the left case. So that'd just be cool. We pull apart the childs from zippers. I might even ignore it here, but you can imagine it's something like that. And we need to return maybe zippers, so we just call I guess we call it unzipper. We have this move up one. That's in our monad, so something like that anyway. But it doesn't recursively move up, so... Maybe we don't actually need a maybe here. So anyways, if we don't take a maybe here, then we can't use the do block. So, bleh. It's looking ugly anyway. We should be able to just do like that, like we originally wanted to when we first started this adventure. There. Because we've got to do something with it, but at the end, we just call on zipper. Actually, that's not even a zipper, just a B. Tree, KV. Yeah, that's looking better. And that'd be our BTree. All right. we could probably just omit it, go point free on it. Bang. So this first function would be zipper. Right. It'll be zip it up. Okay, then we got to do something with that function. Oh, I'm missing some contexts. Or K, show K probably, because I used show somewhere, which we'll need to clean up. Yeah, okay, that's better. Yeah, okay, so then we have this hole here, zipper to zipper. The first operation we need to do is we need to find the key. Then we got to do something else with that zipper. And that's what I need here. Hey, Jake had a cake. What is always gray? What is it? Maybe I can help you. Gray, G-R-A-Y? I don't know. Let's, why is it always gray? I don't know. Sikora, why is it that way? Alan Dillman says, it isn't. We are mistaken. Not everywhere, and not always. It's sunny where he lives in winter, in Canada. What am I doing? I'm hacking in Haskell. We're building a KeyValue database from scratch for the learnings. What am I trying to learn? I'm trying to learn how to build a KeyValue data store, for one, but two, I'm really interested in particular in how we can address like large amounts of memory, hopefully off heap in Haskell. And yeah, how we can do that. So just playing around with it. Also, you know, when I first started this, I was kind of like, I couldn't find a whole lot of streamers doing Haskell. And wanted to have more of them out there. So it became the change I wanted to see. And now it's just a fun way to make sure that I always kind of work on my side projects and don't slack off. But yeah, no, we're building a database for now. And once we get done with this, I don't know, who knows? Maybe I'll start streaming some of the open source libraries I contribute to, or we'll find a new project to work on. Who knows? Maybe we'll just keep working on Rosby because someone will actually use it. All right. Open Skull. Oh, that's my call. I have a call sign. Someone gave me a call sign. It was Quasar. Yeah. Right, so we got a function here that takes a maybe zipper KV and has to get back a zipper. So this is kind of where we get a little bit funky with our composition because of the maybes. Should be too bad, hopefully. Thank you, Jake had a cake. I appreciate that. Reverse fishy, maybe? I want to turn that maybe zipper into a zipper. which may not work with my dot composition. Oh, unless I didn't import it, that would make sense. There we go. Sort of. Yeah, I might have to like putz around with these fun friends. Let's see. What's this type error here? So this is where my compositions are going to get a little bit annoying because of the mix in types. So how can I fix this? Maybe it's not reverse fishy I want. Am I going to start chaining together with functors inside of here? Nope. That's not the right type I want for that hole. That's a maybe zipper KV to KV. I kind of want to peel that maybe off from find here so that I can give it to, say, move up. Or move down, or our to be decided merge up. That's going to actually do the splits and merges. Or zippery insert. Well, we can leave that for another time because we got to implement the zippery insert. Whatever I want to put there, however it composes, merge insert, or insert merge with merge, something like that. That one is going to have subtype like this. It'll have to take those two key value parameters as well. That makes sense. Doesn't technically have to return a maybe. Could just return a zipper KV. I think I might want to do that just so that composing together the other operations that do have maybe in the return type will be easier. So this is the thing I want to put in here. I just want to get the composition right with the types. I have foiled you. That's how I go. I am a confusing and mysterious being. So originally my background is gray. Yeah, I don't know. I like the color scheme. The default for Emacs Prelude. I haven't really changed it because I don't, as we've discovered, I don't like configuring things very much. Although I probably should. Yeah, I don't know. I like the gray. It's okay. Yeah, okay. So insert with merge is what I want to put there. Now, how the heck do I get the... I haven't really done this before where I'm trying to compose maybe returning functions in the middle of like a dot composition pipe here. thought a reverse fishy might be what I was looking for, but I don't think it is. Let's not be fancy then. Let's see if we can just make it work together. So initially we want to take the point free off, and we'll put our root node there. Pass that out, and we pass it off to something else. When we pass it off to, we pass it to find key. Insert with merge takes two parameters, of course, the key and the value. All right, but if we put a hole here, the reverse, where reverse fishy thingy is. Oh, it wants a zipper to maybe list of crumb KV. Well, that's no good. Ah, Jake had a cake. It is the best, dude. I wish you luck, if you are, dude. And Bando, I don't know. Gotta chill, man. Gotta chill. I will never mock somebody for their bad typing, but I will mock them for their other reasons. Sexism's not welcome here. Misogyny's not welcome here. Saying really bad, idiotic things, not terribly welcome. Yeah, okay. Bye-bye, Jakey. It's nice chatting with you. I hope you stop by again sometime when you're a little more sober. Have a good one. Out. Be gone. Doesn't sound like a nice person. It has some issues. Maybe it can be better. Yeah, I'm quick. Quick on the trigger. I'll try and be quicker next time. We'll see. Be like the Mandalorian. Pow. Gone. Banned. Okay. I'm on time. I got 5 minutes left, so... Oh, what is it I'm looking for, Chan? It's not this one. I try to compose them together this way. It's not quite that. Is it reverse bind, maybe? Nope. Okay, let me do a little hoogling. This is where Hoogle might come in handy. We want a function that goes from maybe some A to a function from A to maybe a some combinator. A little slow there. Functor. That might be okay, so we're just passing the value in the maybe along. But we need the function, because we take the value in the maybe as input to the next function. So I don't think that one's quite it. Let me look up control.monad. Yeah. Something sort of like this. All right, when we give it those two functions, it gives us a function back from A to M of C. Right to left collides the arrows. It's... I think that works in isolation, but it might be because of passing to unzipper. Like if I got rid of unzipper, yeah. Yeah, this would be a function from zipper kv to maybe v. That's what I was hoping for. All right, so insert with merge here. Key and value. Right, and then we gotta strip off that maybe at the end to get just a BTree kv. Or we can't do that safely because we still have to handle the nothing case. I'll have to think about that more. Somehow we got to do that. Just to make it compile so we don't leave it in a bad state. Let's just put it like this. All right, then we got to F over it with yuck. There you go. Double FMAP. So this isn't right. I'm just going to leave a little to do in there for me. We need to... I want to remove. Maybe. And then we have to define insert with merge, which we will do next week. Unless I get to it between streams, then I'll just catch you up on how I did it. But there you go. Half finished. Now, it's mostly just combining together the parts and insert with merge. We might have to do a little bit of work on that. But this is why I think this is getting kind of nice now, because insert is mostly just composing together the parts. And the meat of the algorithm can be talked about in isolation. And even in that, on all those diagrams we've seen, that it can, help us visualize how this algorithm is supposed to work. We talk about it in terms of those operations, like finding the node we need to insert to, splitting and merging up, and things like that. And what I'm really liking about zippers so far is that those pieces of the algorithm we can express in little tiny chunks and then just compose them together. And that's like one of my favorite things about functional programming, is just composing little programs from little tiny parts. Yeah, I think we've passed the kind of brain thinky, I don't know what I'm doing hump. And so we're getting closer and closer to kind of getting a better, more clear picture of how this is supposed to fit together. So yeah, I'm feeling a little bit better about it now. It was good. Usually I find it takes like 2 implementations of something before you can really kind of go, oh, this is the way it should be done. This is a nicer way of doing it. So not too shabby. Well, we'll see you next week, hopefully at the regular time on Tuesdays. If you're watching on YouTube, give me a subscribe. If you're just tuning in here on Twitch, every follow helps. Trying to raise the reach of Haskell, and may your monads be free, and may your types always check. And I'll see you out there. Take it easy, Swarm Collective. Bye, everybody else. I'll see you soon.